Alright, so if you're still with me on these review videos, you're on the last video. This is where we're going to talk about empirical formulas and molecular formulas, which kind of just sums everything up that we've been talking about so far. So let's talk first about empirical formulas. Okay, so an empirical formula is basically, and I'm just going to write this out, it's the simplest ratio of atoms in a compound or a molecule. Okay, so an example would be, I'm going to give you two different compounds here, two different formulas. We have CO2 and we have C2O4. Okay, two different compounds here. Let's put a line down the middle. All right. So a couple things that you might notice about this is that the number of carbon in each compound is different, right? 1 carbon to 2 carbon, 2 oxygen to 4 oxygen. But you will also notice that they have the same ratio, and this is the key. Same ratio. So if you were to multiply this by 2, you're going to get that, right? Same ratio. It's a 1 to 2 ratio of carbon to oxygen. I'm going to get rid of this. Okay? So, this is what you call the empirical formula because it's the simplest ratio. There's no way to reduce this any further. No way to reduce it. This is what you call a molecular formula. Whereas they both have the same ratio, the molecular formula is not at its simplest form. Okay? You could reduce this. If you divide it by 2, then you're going to go back over there and get the empirical formula like we talked about a second ago. So, empirical formula is not reducible. Molecular formula is reducible. Okay? I'm going to do bullet points here. Okay? Empirical formula, well, it tells you what's in the compound and it tells you the ratio, does not tell number of atoms. Okay, and I'll explain this in a minute. Whereas a molecular formula, that does tell the number of atoms. Okay, so empirical formula tells you the ratio, doesn't tell you how many atoms of each thing. The molecular formula does tell you how many. So let's say we have ethane. Let's say we have the compound ethane. So ethane has the empirical formula of CH3. That's the ratio of carbon to hydrogen. However, its actual molecular formula, that should be an H, an F. The actual molecular formula of ethane is C2H6. Okay? Ethane is C2H6. So the molecular formula tells you the actual molecule, while the empirical formula only tells you the ratio. So there is a difference there, although both are valuable. Okay? Now, one thing you should keep in mind is that for ionic compounds, and this is going to simplify things for you here. For ionic compounds, empirical formula equals molecular formula. Okay, you may remember when we were going through the chemical formulas section, I told you if you are solving something like, if I told you magnesium oxide, you did this whole deal here, Mg2O, O2 minus, and then you crisscrossed here, and you got Mg2O2, and I told you if you write that as an answer, I'll yell at you because that's wrong, because it's reducible, right? That's wrong. Switch it to that. Okay, now I'm telling you the reason that you do that is because for ionic compounds, the empirical formula equals the molecular formula. The empirical formula is the molecular formula. Okay? This formula right here is empirical. It's the simplest. You have a 1-to-1 ratio. Okay? Can't get any simpler than that. Which is why this guy here is wrong. 2-to-2 ratio, you can simplify that. So for ionic compounds, the empirical and molecular formula is the same thing. So before we go too much into molecular formulas, we're going to talk about how to find the empirical formula. Okay, continuing on, we're going to talk about how to actually calculate this empirical formula. So let's say you are a scientist working in a science lab, and you have a sample. You run it through some tests, and it tells you that it's. Hang on. It tells you that it's. Let me think of a good example for you guys to use. Okay, so let's say we have you run this through the test, and you have 12.57 grams of hydrogen, 37.44 grams of carbon. Okay. Well, now as a scientist, it's your goal to identify what this compound actually is. Now your machine isn't going to tell you what the compound actually is. It'll tell you this. It'll tell you how much carbon's in it, how much hydrogen's in it. It's your job to figure out what the actual chemical is, which means what you're trying to find is the empirical formula. Okay? You're trying to calculate the actual ratio of carbon to hydrogen. So this isn't super difficult. Okay? What you need to do first is convert grams to moles. All right? So let's say we have 12.57 grams of hydrogen. You guys should be pros at this by now. We're converting grams to moles. All right. In 1 mole of hydrogen, there are 1.01 grams, which means that we have a lot of hydrogen. 12.45 moles of hydrogen, to be exact. Okay? So we've got moles of hydrogen. Now we need to find moles of carbon. So 37.44 grams of carbon. That's going to frustrate me. 37.44 grams. And we're going to convert this to moles. So let's get rid of grams. In 1 mole of carbon, there are 12.01 grams. Okay. Put that in the calculator, you get 3.117 moles of carbon. Okay, so that was step 1. We found out how many moles we have of carbon and hydrogen, because that's the important number, as I mentioned earlier. So step 2, find mole ratio. So we're going to find the mole ratio. And to do this, you're going to divide both mole amounts by the smallest mole amount. Okay? So we have 12.45 moles of hydrogen, and we're going to divide this by the smallest mole amount, which was this right here. That's our smallest mole amount, 3.117. So we're going to divide it by 3.117 moles. Okay? And what this tells us is our ratio for hydrogen is going to be 3.994, which this is so close to 4 that for the purpose of empirical formula calculations, we round it to 4. So what that tells us is we have 4 moles of H as the ratio number. So we're going to do the same thing for hydrogen. 3.117 moles of hydrogen. I'm sorry, of carbon. We just did hydrogen. Now, if you notice, as you write this, clearly this is going to be 1 because you're dividing the number by itself. Okay? And that's why we divide by the smallest number, so that one of our ratios is always going to be 1. So what that tells us is we have 1 carbon for every 4 hydrogens. So our empirical formula is C1H4, CH4, which is methane, incidentally. Okay, so that's one example there, and I'm going to get another one in just a minute. Okay, so let's try another one. Let me extend the page here. Okay, so let's say you have 18.29% hydrogen. Let's say you're given a percent composition, and 81.71% carbon. Okay? Well, if you remember in our last problem, we started out with grams, right? So we just started out by converting grams to moles up here. Well, we don't have grams right now. So what you do if you end up in this situation, all you got to do is assume that you have 100 grams of your compound. Assume 100 grams of compound. And just switch these percentages directly to grams. Okay, and that way you have the same number. So that means you have 18.29 grams of hydrogen, 81.71 grams of carbon. So you're not literally converting percentage to grams, you're just writing it this way so that you can solve the problem, and it works the same. Okay, so step 2, we'll do what we did before. This was step 1 in the last problem, converting grams to moles. So we have 18.29 grams of hydrogen, converting grams to moles, 1.01 grams of hydrogen in 1 mole, means that we have a lot. We actually have 18.1 moles of hydrogen. Okay, so let's do the same thing for carbon. 81.71 grams of carbon. Okay, grams to moles. In 1 mole of carbon, there are 12.01 grams. So that means, let me put this in the calculator. You have, in your compound, 6.80 moles of carbon. Okay, so that's what we got for our moles. Now we want to find, and I'm going to switch colors here. Now we're going to find our mole ratio. So we're just going to divide each mole amount by the smallest mole amount, just like we did before. Okay, so we have 18.1 moles of hydrogen divided by 6.8 moles. And you're going to get, hang on, you are going to get 2.66. Okay, so let's hang tight right there. So let's do the same for carbon. 6.8 divided by 6.8, taking some shortcuts here. And we're going to get 1, obviously. Since it's a small number, you're just going to get 1. So what this means is the empirical formula for our compound is going to be C1H 2.66. Well, we can look at that and tell that doesn't really make a whole lot of sense, right? You can't have a decimal there in your empirical formula. So let's get rid of that. We know that's not right, but we did solve our problem right. So what you need to do at this point, which you'll end up with a lot, you have to multiply this number you have here, particularly this one, by the smallest whole number that can make this be a whole number. Okay, and I'll show you what I mean in a second. So if we have, oh, hang on. So there's more than one way to do this. If you can look at it and figure out what whole number that's going to be, that's fine. We can do trial and error. So, 2.66 times 2, is that going to give us a whole number? So you can try that. Multiply that by 2, you get 5.32, so that doesn't work. So let's try 2.66 times 3. You can put that in your calculator. That's going to give you 7.98. Now, like I told you guys earlier, I think I mentioned this, if it's within 0.1, then you round to a whole number. So that's really, really close to 8. Okay? So, what we do now, this is going to be our multiplying factor there. So let me get rid of this here. Okay? Alright. So we're going to multiply this whole thing by 3. So that means the carbon and the hydrogen. So we multiply 2.66 by 3 and we get 8 hydrogen to every 3 carbon. Okay? So now we got whole numbers, so this looks a lot better for a chemical formula. Which means our formula is C3H8, which is propane. Okay? Propane. So we did this basically the same way. The only differences were, and there were two, we converted percentage to grams up here for step 1, and then down here at the bottom for step 4, which I didn't write a 4, we had to convert these nasty decimals up here into whole numbers. Okay? So obviously when you're writing an empirical formula, always need to have whole numbers. Okay, so I want to give you guys one more example problem for you to work through to see if you can do it by yourself now. So let's say you're given 92.2% chlorine, 7.80% carbon. So these are the results from the lab. It's your job to identify the empirical formula by doing the calculations that we just did. So go ahead and pause the video, work through the problem, and then I'll give you the answer. Alright guys, for the sake of time, I don't want to make this video like an hour long, so I'm just going to give you the answer. This should be carbon tetrachloride, CCl4. Okay? CCl4. Okay, there is one last thing left in this unit. We're almost done. So, I want to talk more about molecular formulas. We just learned how to do, or reviewed, hopefully, how to do empirical formulas. So, for molecular formulas, let's go back to a couple examples. So, let's say we have H2O, which is the empirical formula, and we have H4O2, which would be a molecular formula, which has the same empirical formula. So this formula is just double that formula, right? Just double that formula. So, we calculated earlier, water has a molar mass of 18.02 AMU, or grams per mole, I'm sorry, we're doing molar mass. 18.02 grams per mole. So, if I ask you, what do you think the molar mass of H4O2 is? Okay, it's going to be double. You're going to do the same thing. 36 0.04 grams per mole. Okay? And it makes sense because you just have double the number of atoms, which is where the molar mass comes from, right? So the molecular formula will have double, if we're talking about a doubled molecular formula, will have doubled the molar mass of the empirical formula. So let's say we had, we're talking H2O. Let's get away from water. Let's say we have carbon dioxide, CO2. Okay? Carbon dioxide has a molar mass of, let me add this up, 44.01 grams per mole. Okay? So let's say we have C3O6. So if you look at those formulas, you can see that we multiplied the empirical formula by 3 to get that molecular formula. So that would mean the molar mass of that molecular formula equals the molar mass of the empirical formula times 3. So all you gotta do is multiply it by 3 to find it, which should be 132.03. Okay? So this is the first important thing to understand when you're talking about empirical versus molecular formulas. Okay, we're going to do a couple calculations, which are really simple when it boils down to it, but the important thing is understanding why and what you're doing when you're doing this calculation. So let's say we have a problem like something like, let me go down a little bit. We'll look at hydrogen peroxide. Okay? The empirical formula of hydrogen peroxide is just HO. Okay? That's the empirical formula. That's the simplest ratio that we're working with. So this is what you're given. Now, the molecular weight of hydrogen peroxide is going to be, let me add that below in the given box. The molecular weight, molar mass, formula weight, same number here. The molecular weight is going to be, hang on, 34.02 AMU. So this is what you'd be given. You have a compound called hydrogen peroxide. It's got an empirical formula of HO. And its molecular weight is 34.02 AMU. Your job is to find the actual molecular formula. Okay? Which is really, the actual chemical formula here. Okay. So, looking back at what we did before, we can find the molecular formula just by finding this number right here. Since we know the empirical formula, we know this. So if we find this, we can use this to get that. And this is a simple thing. This calculation is simple, but you really need to understand what you're doing and why for it to work. All right. So we know the molecular weight, and we can find the empirical, the molecular weight of the empirical formula. So the formula you're going to use to solve this is going to be molecular weight divided by the molecular weight of the empirical formula. Okay? And you're doing this, when you put that in, it's going to give you this number right here. Okay? It's going to give you that number because you're just dividing the weight of this by the weight of this. And that'll give you that. Okay? So let's try it. So our molecular weight was given to us, 34.02 AMU. And the weight of our empirical formula we can just add up. It's O and it's H. So it's going to be, adding H to O, it's going to be 17.01 AMU. Okay? So we divide those, and you get 2. So that 2, like I keep referring back to this, that's going to be the number that goes here, or here. Same deal. So when we get that 2, we multiply this compound by 2 to get to the actual empirical formula, or the molecular formula, I'm sorry. So our empirical formula times 2, and we're using this 2 here. Okay, empirical formula times 2 equals molecular formula in this case. So our empirical formula was OH times 2 gives us, and we're going to write it this way, H2O2. So this is hydrogen peroxide, which you may or may not be familiar with at this point. So that's how to calculate the molecular formula from an empirical formula. And I'm going to give you guys one example to go through, and then we will be done. Okay, so let's say you have another problem, and we're going to be given the same thing that we were earlier. You have an empirical formula of CH2F. So that's your empirical formula. Now, the molecular weight of the actual compound is 66.06 AMU. So this is what you're given. Now the problem is going to ask you to find the molecular formula, given the molecular weight and the empirical formula. Okay? So we're going to do it just like we did before. We take our molecular weight, and we're going to divide it by the weight of the empirical formula. Okay? So the molar mass, or molecular weight, or whatever we're going to call it, of EF, empirical formula. It's going to be 12.01 for carbon, 1.01 times 2 for hydrogen, and 19 times 2. No, I'm sorry. There's one fluorine. Okay. We add all of those up, and we're going to get, let me put this in a calculator because I've become lazy, 32.02. I'm sorry, that's a 3. 32.03. Okay? And I said molar mass. We're going to do formula weight, just so we have AMU. Okay. So we're going to divide that here. 32. Hang on. 32.03 AMU. Okay. So put that in your calculator. 66.06 divided by 32.03. And you get 2.06. Something like that. Okay, so that's your ratio. Now again, anytime you're working with results from a lab, it may not be exactly accurate. So we're talking about this number right here, not super accurate. But we are within 0.1 here of a whole number. So we're going to round that to 2. Okay? So 2 is going to be the number that we're going to have to multiply our empirical formula by to get our molecular formula. So your answer is just going to be C2H4F2. Okay? C2H4F2. And I'm going to draw this one for fun. C2H4F2. All right. That is it for the review videos. If you have any questions about this, whether it's after the quiz or before, because you're still going to need to know it for the midterm and the finals and all that, please let me know. I would advise working through the problems on the study guide as well. But if you do have any questions about the problems on the review videos, please let me know. All right, thank you for watching.